Hello, my name is Hanjun, and this is Lab 3 Circuits for Physics 2211. So the purpose of this lab is to predict circuit behavior and build a circuit with resistors, capacitors, and batteries in series and in parallel mode to analyze behavior of our circuit with different implementation. And here are the preview of results for the three parts of our experiment. Before we get into the experiment, I would like to go over fundamental principles used in this lab. So first, we've got Ohm's law, which states that the voltage of a circuit is equal to the current times the resistance, and you can manipulate the variables to solve for a specific value. And the most important one here is the conservation of energy and charge, which can be divided into two rules, and they have another name, Kirchhoff's node and loop rule. So the node rule states that the current going into a junction is equal to current going out of a junction. And the loop rule states that the change of voltage in a closed circuit or a closed loop within the circuit must equal to 0. And last, we have the capacitance formula, which states that C is equal to Q divided by V. So here are some initial conditions and assumptions. So for our initial condition, we stated that system is a circuit, everything else is its surroundings. We have two 1.5 volt batteries, two ammeters, and two resistors, which are separately 47 and 100 ohms. For part 3, it will be same two batteries, two bulbs in 10 and 20 ohm resistance, and a 1 Faraday capacitor. The only assumptions we made is that we assume ammeters and wires are fully conductive, so they will have 0 resistance. For part 1 of the experiment, we're trying to predict current flowing through the circuit. So we build a series circuit with the following materials, and we predicted the current will be 0.0204 amps by solving 3 divided by 147. The 3 we got from the reading of the voltmeter, and then the 147 is the combined value of the two resistors. And when we reverse the connection of ammeter, it will show a negative value of our prediction. And so the delta V across the 47 ohm will be like the voltage across the 47 ohm resistor will be 0.8 volts, and the change of voltage across 100 ohms will be 1.8 volts. So in part 2 of the experiment, we use the same circuit we built in part 1, and now we're trying to calculate the actual resistance value for both of the resistors. So in part 1, we calculated that the delta V across 47 and 100 ohms resistors are the following. So we use that and divided by what we got for our current, and we get 39.22 for the first resistor and the 88.24 for the second resistor. When we use our loop rule, it doesn't actually, the change of voltage doesn't actually equal to 0. So our measured volts are less than our predicted volts. And here's our chart. As you can see, after it dropped 0.8 volts during 47 ohms and dropped 1.8 volts when going through the second resistor. So in our third experiment, we built a RC circuit, a resistor capacitor circuit with 10 and 20 ohm light bulbs, two 1.5 volt batteries, and a capacitor with 1 Faraday capacitor. So the discharging time should theoretically take longer because discharging current occurs through the bulb. And here's our time. And as you can see, our times is the opposite of what I said earlier in this statement, and that could be due to human error. So here are some potential errors we made in the lab. So human timing errors in part 3, including recording timestamps and recording voltage using ammeter. Ammeter, we could have our reaction is not exactly as when the light bulbs are charged and discharged, and we could have incorrect voltage readings, either due to incorrect placement of the pins or potentially faulty multimeters, therefore contribute to inaccurate readings. So some additional questions. So the ideal model would predict the capacitor reaches full charge instantly. So we are given the ideal model of capacitor charge. It says that the change of the voltage is equal to the change of initial voltage times the charge to the power of the charging time constant. So if we set the resistance equal to 0, then the entire exponent is 0, therefore saying that the charges occurred instantly. And for the second part, if we measure charging time using ammeters longer than the ideal predicted time, so ideally, charging will occur instantly because there are no resistances. However, that's not going to happen in the real world. In a real world circuit, there's always going to be some sort of resistances. So therefore, as current passes through resistances, current gets weaker and slower. So therefore, charging time will not be instant. It has to be an actual value. Thank you.